Hey everyone, Dave McMillan here, lecturing today on engineering drawings in part one. Got original assistant here, still hanging out. Say hi. All right. Hey, keeps me focused. Yeah. So we're going to jump right into it. There's a pretty short slide deck for this, mostly on drawings and communications with drawings. We're talking about engineering drawings. What is an engineering drawing? I'll give everyone a moment to ponder the question, but the answer comes pretty quickly. There's a sort of complicated answer here and a simpler answer. We'll just go with the simpler answer, as we want to convey the information necessary for the component to be manufactured and meet its original design goals or intents. Drawing can do a bunch of other things too. It can be a contract between a designer and a manufacturer. So as an engineer, you would present a drawing to a manufacturer. They would bid on the drawing. They would produce a quote. You would say, we need 2,000 of these a week indefinitely. And they would tell you how much it would cost them to do that. And then when you entered into a contract, that drawing would be part of that. And if you needed to make a change, it might affect their manufacturing process. And there would have to be a renegotiation about price and so forth. So it can be part of a contract. It can be a record of a design. So if you're going through multiple iterations of a device, that gets recorded in a drawing. And there's usually spaces and standards for how to do that. It's a tool for documentation and tracking changes to a design. So it's a collaboration tool that multiple people can put input into. It's a documentation of compliance with requirements. In this case, for example, the medical device manufacturer, the drawing itself will contain documentation, evidence, and references to standards and references to tests that were performed about the particular part. And it can be proof of intellectual property, so it can be part of a patent claim. A drawing is not a sketch and it's not a model. But both of those are useful, and here they are. These two parts are the same. The sketch and the model are both the same. And we could have a formal drawing that sort of sits in between these, or afterwards. So in a modern format, I might sketch this figure out on the left here and say, I need these 4 tapped holes in the center and these 4 clearance holes on the outside, and the plate needs to be this dimension. And then I would render this up in CAD package on the right there. And then a drawing would come after that. The CAD package would help me produce a drawing. And then I could put other information in it about who I was and how many I wanted and what the various tolerances were and so forth. But we try not to mix these terms up. We want a sketch to mean a hand-sketched thing, a model to mean a computer parametric representation in 3-dimensional presentation, and a drawing to be a 2-dimensional technical representation that's sufficient to either recreate a model or move to manufacturing. What features do engineering drawings have? There's a lot, but the ones you'll see the most are lines, dimensions, and holes. Lines can be object lines, center lines, hidden lines, and section lines. Those are all color-coded for you here. They have a dash format in there. There's a standard that you'll see for drawings, technical drawings. And a lot of drawings, I think there's one later in this presentation, will reference that standard and say these lines are presented in compliance with a standard. As are the tolerances and the hole types and so forth, are covered under these drafting standards. So here's a top and a side section view of 4 different types of holes with representative callouts. As we talked about earlier, please don't specify that flat-bottomed hole unless you have an absolutely good engineering reason to do a flat-bottom hole. Otherwise, do a drill point hole, like the 3rd one there, or a through hole. The only really good engineering reason you'd need a flat-bottom hole is to say something like this plate needs to have a precision pin of a very specific length set in it, and the top of that pin needs to be a certain height above the plate. And then you would need a flat bottom hole because you have to clock that reference in Z very accurately. And you would probably call that out on a note so your machinist isn't tearing their hair out. trying to get that whole flat bottom for you when they suspect that you don't need it. But if you tell them, if you tell a machinist, I absolutely need it this way, you'll get it. It's just that there's a price and time. This is another thing about a drawing is that it should have only the dimensions it needs. It shouldn't be over-dimensioned and it shouldn't be under-dimensioned. You should be able to completely manufacture it by referencing each number one time, so to speak. This is a drawing I did some years ago now, which is a Teflon Petri dish, essentially. It's a Teflon dish for holding a microscope slide, which is 1 inch by 3 inches, and covering it with the minimum amount of an extremely aggressive etching acid that the Teflon was tolerant to, in order to get the slide really clean. And we have a couple of clearance holes for tweezers to pull the slide out. It's made out of Teflon. So as you can see on the left there, I've got the full thickness I want. I describe the depth of the pocket that's in there. I give my machinist the stock on the side. So I say, I'm providing you this stock and it's this diameter. You don't need to do any machining operation. That's a great way to save a lot of money and time, is to machine out of stock on your first major dimension, which in this case would be the diameter of this rod. And then I describe the pocket. I use some center lines, set up the radiuses, give them all the additional dimensions. Down on the bottom, I tell them where it's coming from, what it's supposed to be made out of, what it's called, what the date is, what my general tolerances are. And then because it's Teflon, it likes to tear. I tell them I need it all to be smooth, so to be conscious of that. And I want 3 of them. Here's a much more complicated drawing. This is from a lab out at Zucro. We got this with permission. This is a part of a stack to test a rocket motor. So this is it's kind of the top part of an injector. There's ports on the side that put in either oxidizer or fuel. You can see that we have to have cross sections. There's finish callouts. It's fairly complicated. There's no GD&T in this particular drawing. We'll cover GD&T in another lecture a little later on. But this one, just to show you where these can head, they can be fairly complex, but this is, once again, fully dimensioned. There are no extra dimensions. And this should have the spec. No, they don't have the spec that they've drawn it to. But you can see something like up at the top where we have 4 by 2 AS5202 port. Well, that's a certain type of port fitting. And the machinist would go look up that port type to get additional information and dimension. Or in this case, the Zucro machinist does these ports all the time, they know. But another machinist, you could send this to any shop in the world capable of doing turning and milling in stainless steel, and they would be able to produce this satisfactorily based on just the technical information on the sheet. So a little bit about measurement as they appear on drawings. All of these drawings have all of these tolerances and measurements on them that we're going to use to both fabricate it and then inspect it afterwards. I guess it's worth stating that this is, the engineer saying up front, we'd like you to fabricate this thing to these dimensions. And then when we get it back from you, we're going to take this same print and we're going to inspect it. Or we're going to send it to an inspection department. And they're going to verify that the physical object contains the same dimensions or is of the same dimensions. And then if that's true, the part is said to be to print. The physical manufactured object is the same as the print. So the part is to print. And if it's not true, then you can send it back to the machine shop and say this part is not to print. And they can say, well, your print is ambiguous and we did this. Or your print is incomplete. Or, oops, yes, we'll fix that. So it's very important to make sure that your print is achievable and it's fully dimensioned. There isn't extra dimension and there isn't ambiguity. So to measure things, we compare the tolerance with a known standard. Or, sorry, the tolerance is incorrect. We compare the quantity of a unit with a known standard of that unit. And there's the inch system and the metric system, and this is a bit of a mess. If I ever get my 3 wishes from the genie, one of them is definitely going to be that either the inch system exists and the metric does not, or that the metric system exists and the inch system does not. Metric is going to win eventually for several reasons, but this is the prominent one. Metric is rational. It's a 10-base system. It scales up and down from smaller than the smallest fundamental particle in the universe to way larger than the universe is thought to be. and it does that in 36 powers of 10 or something like that. It's all completely contained in a pretty small numerical space. And it's used everywhere except present party, and Myanmar, and I can't remember East or South. I can't remember the name of the country in Africa has not yet ratified the SI, the United Nations SI agreement. But that's about it for the engineering drawings. Thanks for your attention. A couple more lectures coming up.